Okay, there are sign conventions, plus and minus conventions, we need to set up more carefully to get the sign of this thing to come out exactly right. Okay? So we need to think about what's happening in a circuit that has a capacitor, initially charged capacitor, a resistor, and an inductor. Okay? But the calculation and the idea is very simple. The inductor, EMF, is negative L di dt. So that's going to be negative L Q naught over RC squared times e to the negative t over RC. Opposing the discharge of the capacitor. Okay? Capacitor wants to discharge, so it pushes the current this way, if this is positive and this is negative, right? But that current's going to be decreasing. So the direction of di dt will be opposite that of the current, okay? And the induced current will then be, well, induced EMF will be this, but in a direction opposing a discharge because it opposes the decrease in the current. Decrease of the charge goes along with the decrease in current. The inductor opposes that.
So just so if it did work out that the sign was supposed to be negative, would that would make that a positive?
Yeah, we'll worry about the signs.
Okay.
But if this is positive, then this is negative.
Right.
Okay? So yes, and if this is negative, this is positive.
Right.
Well, we'll
But
put
that just
signs
has to
on
do
everything and clarify this in a minute.
Okay.
Okay? Just by common sense looking at the current and the signs of everything. Okay?
Right.
Okay, so in any case, you're going to have this, right? Now there's a problem with this because the e to the negative t over rc, v naught e to the negative t over rc, or q naught e to, whatever, is based on the idea that your voltage drop across the resistor is equal to the voltage drop, the increase in voltage across the capacitor. Again, so that as you go around the circuit, you have a zero voltage, right? If we throw an inductor in here that's opposing that, then this no longer applies. Okay? And in fact, if L is big enough, our result here could be that the EMF that you get here is greater than the voltage of the capacitor. And it can't be. Because the inductor, when you close a circuit to start discharging the capacitor, there's no way the inductor is going to make current go the other way, unless it's already charged. No way an uncharged conductor. Okay? You can have an inductor that already has a current in it, and that will drive things in whatever direction. Okay? But if you have an initially uncharged inductor here, it's not going to develop an EMF that drives current the wrong way. The only thing driving the current is this, and all the inductor can do is oppose the change in current. And what this means is that you're going to have a slower change. Okay? It's going to retard the discharge of the capacitor and slow things down. Okay? So let's go ahead and write it out now with the LRC circuit and all the plus and minus signs and everything, and make sense of the sign conventions that we were a little careless with here, that I was a little careless with. Okay?